Good morning. Morning, everyone. Oh boy, I'm just really tired this morning. Gonna wait for a couple more viewers. All right, cool. Hello. I'm gonna go ahead and get started. So, today's lesson is about uncertainties. So let me just give a quick review of last time. So last time what we learned is that when uncertain measurements are added or subtracted, they're absolute uncertainties. Add. So if things are added or subtracted, doesn't matter if they're we don't subtract the absolute uncertainties. We always add them. Okay, the absolute uncertainties add. So let's just do a really brief example just to remind you guys how that worked. So what if we had x equals 4.1 plus or minus 0.4, and then we have y equals let's say 2.5 plus or minus 0.6. Okay, and we want to quote a value for 3x minus y. Okay, so 3 is just a constant. So when we multiply by 3, it is going to take the best guess and multiply it by 3, and it's going to take the absolute uncertainty and multiply it by 3. So 3x is going to be, so multiplying 4.1 by 3, that would give us 12.3 plus or minus 1.2. Now technically I should now round this, but I'm going to wait until the very end of the calculation to do the rounding. Okay? So now I have 3x minus y, so that's 12.3 plus or minus 1.2 minus 2.5 plus or minus 0.6. So what we'll do is we'll take our best guesses and we'll subtract them. So 12.3 minus 2.5 is going to be 9.8. And then with our uncertainties, we're going to add them. So even though it's subtraction, we still add them. So we have 1.8 is 1.2 plus 0.6. Okay, so we would get plus or minus 1.8. Now, technically speaking, I should round this to one significant digit. So I would round the 1.8 to 2. And then this uncertainty is in the ones place. Okay. And so I would round this to the ones place and make it 10. All right. But when you're doing the homework, you don't have the ability to, I don't have the ability to round it. And so this is what you would type in on the homework. Okay. All right, so that was last time. This time, what we're going to learn how to handle is situations where we are multiplying quantities. Okay. So let's suppose that we had two quantities, x and y. So I'm going to make some new quantities. So maybe this is 3.1 plus or minus 0.2. And this is 8.5 plus or minus 0.3. Okay. And we want to quote a value for x times y. So what do we do if we want to quote a value not for the sum or the difference, but for the product? Okay. And so this case is a little bit trickier. So what we want to do, okay, first of all, our best guess is going to be just the product of these two. So it's going to be 3.1 times 8.5, as you would expect. Which is 26.35. Okay, but now we have to deal with the uncertainty. Okay, and so here's the rule. When uncertain quantities are multiplied or divided, okay, the fractional uncertainties add. Okay, so if things are added together or subtracted, it's the absolute uncertainties that add. But if they're multiplied or divided, it's the fractional uncertainties that add. Okay. So that is the major difference. So what I'm going to do is I'm going to go ahead and compute the fractional uncertainty in x. That's going to be, remember, the definition of fractional uncertainty is absolute uncertainty divided by the value. So 0.2 divided by 3.1. So the fractional uncertainty in x is going to be 0.2 divided by 3.1, 0.065. And then the fractional uncertainty in y is going to be the absolute uncertainty divided by the value. Okay. So 0.3 divided by 8.5, which is going to be 0.035. Okay, so what that means is that the fractional uncertainty in x times y is going to be the sum of these two. So it's going to be 0.065 plus 0.035. So that's 0.1 is the fractional uncertainty, okay, in x times y. So when we are quoting a value, we typically quote the absolute uncertainty. So now what we need to do is we need to turn the fractional uncertainty into an absolute uncertainty. So I know that so that means that the absolute uncertainty in x times y is going to be our best guess times the fractional uncertainty. See how if we take, for example, this equation and we multiply our fractional uncertainty by 3.1, we get back our absolute uncertainty. So it's just rearranging this equation. So I take my fractional uncertainty and I multiply it by my best guess, which was 26.35, and I get 2.635. Okay, so I quote a value. It's 26. So x times y equals 26.35 plus or minus 2.635. So now I'm going to round this, which you won't do in your homework, remember, but when you write an IA, that's what you want to do. So I round this, and this rounds to 3. Okay. So I round it to one significant digit. That significant digit happens to lie in the ones place, and so therefore I round my best guess to the ones place, and that gives me 26 plus or minus 3 is a quoting a value for the product of those two. Okay? I think you can see the whole thing. There's nothing that's not visible. Okay, so this is our big rule for today. Now, for example, and I'm just going to continue along. Let's do one more example. Okay, just at the bottom of the page. What if I wanted to quote y to the third power? Okay. Now you might say, well, this is a power, so it doesn't really fit into things being multiplied or divided or whatever. Okay. All right. But we can think about y cubed as y times y times y. Okay. So what that means is that the fractional uncertainty in y cubed is going to be the fractional uncertainty in y plus the fractional uncertainty in y plus the fractional uncertainty in y. So if you raise something to a power, you need to multiply the fractional uncertainty by that power, because you can see that I raise it to the third power and I have 3 fractional uncertainties added together. So that's going to be 3 times the fractional uncertainty in y was 0.035. So that's 0.105 is my fractional uncertainty in y cubed. Okay. All right. And so now, what's going to be my best guess in y cubed? Well, my best guess is going to be the actual value of y, which was 8.5 cubed. So that's going to be 8.5 cubed. Which is 614.13. So what does that mean about my absolute uncertainty in y cubed? Well, it's going to be 0.105 times 614. Okay. And that gives me 64.48. Okay. Which I would then round to one significant digit, so I would round that to 60. And that means I have to round this to the tens place, so that would be 610. So my quoted value for y cubed would be 610 plus or minus 60. Okay? So if you're not getting it yet, don't worry, we're going to do lots more examples. All right. So let's do an example. Let's say a car completes a race in t equals 9.75 plus or minus 0.04 seconds. Okay, the race is let's say 400 plus or minus 1 meter. Okay, what was the average velocity? Okay, what was the average velocity? So first thing we want to do in this case is we want to get a formula. Okay, so the formula for average velocity is distance traveled divided by time. So this is division. And remember, when things are multiplied or divided, their fractional uncertainties add. So I need to find the fractional uncertainty in x, and I need to find the fractional uncertainty in time, and I need to add those two numbers together to get the fractional uncertainty in velocity. Okay. So for x, it's going to be 1 out of 400. And for time, it's going to be 0.04 out of 9.75. So this is 0.0025. And this is 0.0041. Okay? So taking these two, that means that the fractional uncertainty in x divided by t, we add their fractional uncertainties. So I'm going to add 0.0025 to 0.0041, and I get 0.0066. Okay? So we figure out what the fractional uncertainty is. Then what we do is we now what we want to do is we want to get our best guess. Our best guess is going to be equal to the best guess in length of the race divided by the best guess in time. So it's going to be 400 meters in 9.75 seconds. So our best guess at the velocity, 400 divided by 9.75 is 41.02 or 41.03 meters per second. So now we need to get our absolute uncertainty in velocity. And so that's going to be 0.0066 times 41.03. Which gives 0.271. Okay? So now what I have to do is I have to round to the correct place value. So I round this to one significant digit, that's 0.03, or 0.3, excuse me. And then this gets rounded then to the tenths place, so this would become 41.0. And my quoted value is going to be 41.0 plus or minus 0.3 meters per second. Okay? So here's the general strategy. Okay? The general strategy is calculate the fractional uncertainty, add them, add the two or three or however many things are multiplied together, add together those fractional uncertainties. Then you want to calculate your best guess. And then lastly, you want to, after you calculate your best guess, you want to then use the best guess and the fractional uncertainty to get the absolute uncertainty. And then once you have the absolute uncertainty and you have the best guess, you quote your value. Okay? So let's apply this again. You drop a rock, let's say 45.7 plus or minus 0.3 meters on an alien planet. It takes 5.26 plus or minus 0.09 seconds to fall. Quote a value for the acceleration due to gravity. All right. Quote a value for the acceleration due to gravity. Okay. So, so what we need to do here is we need to figure out the equation. All right. And this comes from kinematics. If I was asking you to find the acceleration due to gravity, you would use kinematics. You would say, oh, well, delta x equals 1/2 at squared. Okay? Delta x equals 1/2 at squared. So that's the equation you would use to get the acceleration due to gravity. So then if I solve that for the acceleration, I can see that the acceleration is 2 delta x over t squared. So I can see that this involves multiplication and division, all right? So what that means is I'm going to be calculating with fractional uncertainties. So the fractional uncertainty in acceleration is going to be the fractional uncertainty in 2 plus, because it's 2 times delta x divided by t squared, plus the fractional uncertainty in delta x plus the fractional uncertainty in t, because I'm thinking about this as 2 times delta x times 1 over t times 1 over t. All right? Now, anytime you have something raised to a power, okay, similar argument to what we had here where it was y cubed, so we just tripled the fractional uncertainty. Because we have t squared, we're just going to double the fractional uncertainty. Okay. So 2 is just a constant. It has no uncertainty, so this one doesn't count. The fractional uncertainty in delta x is going to be 0.03 divided by 45.7, or 0.3 divided by 45.7. 2 times the fractional uncertainty in time is 0.09 divided by 5.26, like that. So that tells me that the fractional uncertainty in acceleration is what I get is 0.041. Okay, so I got my fractional uncertainty. Now what I need to do is I need to get my best guess. All right, so my best guess, acceleration is 2 times delta x over t squared. So I use all my best guesses. So my best guess at delta x is 45.7. My best guess in time is 5.26. And this gives an acceleration due to gravity of 3.30 meters per second squared. So now the question, and I'll write it as 3.3035. So now the question is, what is the absolute uncertainty in acceleration. Okay? The absolute uncertainty in the acceleration is going to be 0.041 times my best guess, which is 3.3035. Which is 0.135, which I then round to one significant digit, so that's going to be 0.1, which means I then have to round this to the tenths place, which is going to be 3.3. So when I quote my value for the acceleration, my best guess is 3.3. My absolute uncertainty is 0.1. So that's our answer. All right. So I'm going to do one more example that kind of throws it all together. All right. By the way, what was tricky about this one is that I didn't actually give you the equation. So you had to use physics to get the equation that you then do propagation of uncertainties on. All right. Okay, one more example. Suppose that x equals 6.345 plus or minus 0.008. Okay. And y equals 2.9 plus or minus 0. Actually, let's make it 102.9. Plus or minus 0.2. Okay? And so what we want to do is we want to quote 2x squared minus 3y to the 1/2 power. Okay? So there you have it. So we're basically going to treat this as two separate problems, actually three separate problems. We're going to quote a value for 2x squared. We're going to quote a value for 3y to the 1/2. And then we're going to combine those because they're subtracted. Okay? So first of all, let's do this one. So my fractional uncertainty in 2x squared is going to be the fractional uncertainty in 2 plus 2 times the fractional uncertainty in x, because x is squared. All right. 2 is just a constant, so it has a fractional uncertainty of 0, plus twice the fractional uncertainty in x. That's going to be 0.008 divided by 6.345. So this is 0.00251. Okay. So now I get my best guess of 2x squared. Okay. So my best guess of 2x squared is going to be 2 times 6.345 squared. which is 80.513, or 518, excuse me. So now what I'm going to do is I'm going to get my absolute uncertainty in 2x squared. So that's going to be my fractional uncertainty times my best guess. Hang on, I think Hazel's getting into trouble. Hazel! Hazel is so desperately hungry lately that she is resorting to despicable measures. Okay, getting that absolute uncertainty. Oh, that should be 0.002. My bad. Absolute uncertainty is 0.202. So, that means, so now I'm going to quote 2x squared. All right? So 2x squared is 80.518 plus or minus 0.202. And I'm not going to do any rounding until the very last step. Okay? So now I have the fractional uncertainty in 3y to the 1/2. Okay? That's going to be the fractional uncertainty in 3, which 3 is just a constant, plus the fractional uncertainty in y to the 1/2. Now, remember, whenever you raise something to a power, its fractional uncertainty gets raised to that power. So this is going to be 0 for 3, plus, because it's raised to the 1/2 power, the fractional uncertainty gets multiplied by 1/2. The fractional uncertainty in y is going to be 0.2 divided by 102.9. So that means my fractional uncertainty is going to be 0.000972. Okay, so now I got to get my best guess of 3y to the 1/2. So that's going to be 3 times 102.9 to the 1/2. Which is 30.43. 30.431. Okay. So now I have to get the absolute uncertainty in 3y to the 1/2, which is going to equal my fractional uncertainty, 0.000972, times my best guess. One thing I want to say is that all these steps are really easily programmed on a spreadsheet or on a computer. Okay, it takes a long time when you do it by hand, like I am, but it's really quite simple when when you do this on a computer. So the place where you're really going to use this stuff is in your IA. And so on your IA, I'm going to show you, I'm actually introducing the IA next week, and I will show you how to do all this stuff in Desmos or on a spreadsheet so that it saves you a ton of time. So now we got to quote 3y to the 1/2. That's going to be 30.431 plus or minus 0.030. Okay, so now we subtract these. Okay, so we're going to subtract our best guess, because remember, our original thing is to subtract these. So we have 2x squared minus 3y to the 1/2. Quoting it, I subtract my best guesses. Okay, so 50.518 minus 30.431 gives me 50.087. That's my best guess. Now here's the thing. Now I am just subtracting. I'm not doing multiplication. So it's not the fractional uncertainties that add, it's the absolute uncertainties that add. So I'm going to take just these two numbers and add them together. Plus or minus 0.0 or 0.232. All right. So now I round this to so that it has one significant digit, which is in the tenths place, 0.2, and then I round this one to that same place, so that's going to be 50.1. So this is my best guess. Or that's my quoting of value. All right, so I will see you.